is on potassium tantalate-based nanoelectronics. Our group is interested in creating semiconductor nanoelectronics based on oxide systems. All the interesting properties that correlated oxides have, such as superconductivity, ferromagnetism, and ferroelectricity, can add richness and utility to our semiconductor devices, and vice versa. Our nanoelectronic devices will give us insight to the underlying physical properties of our oxide system. And our group is mostly interested in lithium aluminate strontium titanate heterostructure. When you have just 3 unit cell of LU on STO, we can tune the metal insulator transition at the interface with conductive atomic force lithography. When you sketch with a positively biased AFM tip on LU surface, it will leave a trace of protons, which can attract electrons to the interface, and thus making the interface conducting. This process is reversible. If you sketch with negative voltage, you can remove or erase where you have just written and restore the interface to insulating, which allows us to create local barriers on our device. And this technique typically has a resolution of 10 nanometer, and it can be repeated many times because it doesn't do any damage to the crystal. Recently, we also developed a technique for creating nano devices, which is the ultra low voltage EBL. When the LU-STO is exposed under electron beam, the interface will also become conducting locally. This technique, compared to conductive FM lithography, has much faster speed and much larger working area. So it's very suitable to creating large two-dimensional devices. And from these two techniques, we are able to make many interesting nano devices such as single electron transistor, quantum dot, terahertz generation, electron, waveguides, all kinds of interesting nano devices. And one other oxide system that gained people's attention in the recent years is potassium tantalate. It's very similar to STO, except the conducting band comes from the 5d electron of tantalum, and the superconducting property is very interesting, since that LU-KTaO3-based has a Tc of 50 millikelvin when gated by electrolyte gating, but LU-KTaO110 and 111 has much larger Tc, which is 1 Kelvin and 2 Kelvin respectively. Also, the superconductivity is tunable by backgate because the potassium tantalate has a really large dielectric constant, close to 5000 at low temperature. So basically, these are the mysteries about this oxide system. And because we are interested in creating nano devices, we want to adapt the two techniques that worked on LU-STO to LU-KTaO. And here we start with an intrinsically insulating LU-KTaO110 sample, and through conductive FM lithography and ULV-EBL, we're able to pattern nanowire and hall-bar devices, which show superconductivity at low temperature and the superconductivity is also gateable at low temperature, and by cooling down a nanowire device, we can see this transport behavior that's similar to a single electron transistor, because you can see this Coulomb diamond features, which represents the electron tunneling. So this verifies the one-dimensional nature of the device we have created. And since we have this superconducting system and we have the ability to create nano devices, one intuition would be creating superconducting quantum interference device, which is SQUID. Usually people use SQUID as a sensitive magnetometer. It constitutes of two parallel Josephson junctions that form a loop between them, and its IV characteristic is very sensitive to the flux through the loop. Is heavily used in transmon qubits, and previously through the hard mask technique, people have achieved this SQUID device at LEO-STO platform, but no SQUID has been realized in LEO-KTaO yet. So we think if we try to create a LEO-KTaO device, a SQUID, with our conductive FM lithography technique, and this is the device we have. Basically, we first read out the large two-dimensional green region, and we cut here and cut here, and after that we reconnect here and here by writing two vertical lines. So we have a upper half of superconducting region and the lower half of superconducting region, and they are connected by two nano bridges to form the SQUID. And this is the IV characteristic of this device. You can see the critical current modulation here, and if you sit at this particular current and monitor voltage while changing the field, you can see the voltage oscillation, and the period of the oscillation is 27.5 oyster, and it corresponds with an effective area which is 0.75 micrometer squared, which is a little bit larger than our middle hole area. This is due to the screening current within this two-dimensional region, and which will cause a phase difference between here and here, and also between here and here. You can also notice one thing is that there seems to be a phase shift between IC plus and IC minus. You can see it more clearly here when you plot the differential resistance. So when in the positive sourcing direction, when the critical current is the largest, IC minus is the smallest. We think this may due to the kinetic conductance of these two nano bridges. We changed the area of our device. We shrinked it by 25% to make the whole 0.21 micrometer squared, and we indeed see the oscillation period increase. It increased to 33 oyster, and which corresponds with an effective area of 0.63 micrometer squared. And you will notice that in this device there's no much phase difference between IC plus and IC minus, which means that which may due to that this separate device may have different kinetic conductance as the previous one. And to compare, we also make a single junction device, single weak link device. We only keep the left junction this time, and this is the IV characteristic. You can obviously notice that the oscillation is gone, and there are a few other things going on here. First of all, you notice that the critical current seems a bit asymmetric. At when the field is positive, the IC plus seems to be larger than IC minus, and when the field is negative, IC minus seems to be larger than IC plus. This may due to both the this may due to the strong spin orbital coupling of this nano bridge here, and people usually observe this Josephson diode effect when they have both time reversal and spatial reversal symmetry broken. And also the other thing you may notice is that 0 Tesla there's a more obvious residual resistance. This can come from something very interesting, such as the P wave superconductivity, but we are not sure yet. This may also comes from some magnetic impurities, which will also cause this obvious residual resistance near 0 Tesla. So in conclusion, we demonstrated the KTaO3-based squid created by conductive FM lithography, and we observed the critical current oscillation when we have two junctions, and we observed some asymmetry of IC plus and between IC plus and IC minus in single junction device, which may indicate a Josephson diode effect, and we plan to investigate more on the Josephson diode effect and the spin triplet superconductivity, the possible spin triplet superconductivity in the following.